WWF, Worldwide Fund for Nature, as it's now called, was founded in 1961, 55 years ago. And it was founded by naturalists who became aware of the fact that species of animals were disappearing and that it was probably humanity's fault that they were doing so. And the thought that a species of animal might be exterminated and gone forever because of what mankind had done appalled those founders, among whom Sir Peter Scott was very prominent. And those far-sighted people immediately set about looking after those particular species that were in particular danger. The Hawaiian goose, the oryx, and for an emblem which Peter designed, the giant panda. We were seeing that these were disappearing as a consequence of what human beings were doing. And the immediate, urgent solution to the problem was seen to be to, where you could create a reserve, put a fence around them. And where you couldn't, you could take them into a zoo or somewhere and breed them up to make sure they didn't become extinct. And they did that. They did it with the oryx. They did it with giant pandas. They did it with Hawaiian geese. And that was fine, up to a point. They then started listing all the others that seemed to be in danger and produced a red list of species that were on the verge of extinction. And so they started creating reserves, quite rightly. But then they began to realize that actually these flagship animals, these spectacular, dramatic, popular animals, were only symptoms of a greater malaise. And if you wanted to really conserve them, you had to conserve their environment. The ecosystem was the important thing. So the gaze, the concern of WWF became, well, it was remaining on this species, but it also began to embrace much bigger things. And as time came by, they began to realize that actually those reserves, those national parks, or whatever they were, big though they might be, were nowhere near enough. That now you had to think about continents. You had to think about oceans. You had to think about the sky. So again, WWF increased its vision. The changes that were going on were increasing in severity. And people started to realize that even though we hadn't catalogued things, there were things disappearing we didn't even know that we'd recognize. So a turning point arrived. When geology was founded 150 years ago, people started looking at the history of the Earth and the history, the fossils, the history of wildlife. And they began to divide the world's history and the history of life on this planet into geological periods. Cambrian, Ordovician, Silurian, Carboniferous, Devonian, you know them all. And what was it that made them think that one era, one period, had come to an end and you were about to start a new one? Well, it varied. What they all had in common, that there was usually a major shift in the kind of animal populations that were alive at the time. Some of those changes were dramatic, like the asteroid, which we think probably, at any rate, was responsible for the disappearance of the dinosaurs. Many were not so dramatic. There were also great volcanic eruptions on a vast scale, much bigger than anything that's happening now. And there were others that were more gradual. So, Now we are facing a new change. Now people have come to realize that the changes that have been taking place on this planet now are actually comparable in terms with the changes which they saw in geological eras. Why? Well, I'm happy to say that we have a great expert here who is going to look at those changes and once more analyze them and see what's responsible and speculate as to what we might do about those changes, for they are taking place now, and the proposition is that we are entering a new geological era. Not as in the past it happened, a change over thousands of years, if not millions of years. Not over, indeed, centuries, as it happened in the most recent changes, but within decades, ladies and gentlemen, within decades, within our lifetimes. It's my pleasure to invite Professor Johan Rockstrom from Sweden to come and tell us about the Anthropocene. Thank you.
Thank you so much, Sir David Attenborough. What a wonderful introduction, and coming after Sir David and Royal Highness Prince Charles, it's enormous honor, and that's absolutely correct. I'll be trying to give you a scientific update of the evidence behind three key insights, in fact. The entering of a new geological epoch, the Anthropocene, that we thereby are leaving Eden's garden, the Holocene, and that we also must now recognize that tipping points is actually part of normality. So we're living in a world of surprise, of turbulence, and the need to reconnect our whole world development to the biosphere. And I must admit personally also, it's also an update not only from a scientist, it's an update from an increasingly nervous science community. It is a sense of dire need to transform not only the way we go about technology and economy and development, but even a mind shift in terms of the values between us humans and our beautiful planet Earth. And of course, nobody expresses this better that I know than Sir David Attenborough. So it's a particular privilege to do this together with you here tonight in this moment of the very significant launch of the Living Planet report of WWF. Now, the scientific summary here can actually be done in two short slides before going in a lot on the numbers and let's say the graphs. And I think we're all today aware, and I'll just start off by making the point that science today can show through empirical evidence that up until very recently, it is in fact even possible to state a year, to 1990, we were still a relatively small world on a big planet. We have so much evidence that our unsustainable development paradigm actually delivered because we had ample atmosphere, ample ocean, ample biodiversity, ample biomes to exploit, and no invoices were being sent back to societies at the planetary scale. But from 1990 onwards, we tip over into what we can today call the era of us being the relatively big world on a small planet. We have in Professor John Schellenhuber, the key leading climate scientist advisor to Angela Merkel, German Chancellor, reached a saturation point. We are actually, as humanity, hitting the biophysical ceiling of the little planet's capacity to support humanity. And it's important to just remember this, that this tipping point occurred as recently as only 30 years ago. And that this can be an explanation why it takes time to transition into the new logic of global sustainable development. But things are changing. It's absolutely clear today, I would argue, that we have so much evidence and it's being understood from policy to business to society at large that we actually live on a human-dominated planet. We are shaping the entire biosphere. And not only that, what the environmental movement, and WWF, of course, being the grand defender over so many decades since 1961, showing that we have an ethical responsibility for nature, but now science shows in its very objective empirical basis that that's not enough. In fact, we depend on nature. Nature builds our financial systems. Nature builds stability and avoids big, unstable refugee crisis. Nature actually is the fundamental reason why we can have prosperity and development on planet Earth. But it all starts, in a journey of ignorance. Once upon a time, on this beautiful island we're on right now, United Kingdom, with the invention of the coal-fired steam engine, which is where we kicked off the Industrial Revolution. And this is a scientific summary of our journey from 1750. On the y-axis you have parameters of human pressures, from biodiversity with the sixth mass extinction to population growth and climate change. And what you see here is the Industrial Revolution started in the United Kingdom in the 1750s, spreading rapidly across the world thanks to infrastructure development, particularly railway. And we start moving into the first 1-2 billion people. We come to the end of the 19th century and we went the Haber-Bosch process, which takes us into modern fertilizer use in agriculture, expanding modern agriculture. And we also, remember, we have Fleming here inventing antibiotics, which enables life expectancy to increase to a point that when we come to 1955, we see a break on the line. Up until that point, we're actually having a very insignificant impact on the planet as a whole, but that's when we take off. We're 3 billion people. It's 10 years after the Second World War. We put in high gear, and we enter what science has now baptized the moment of the great acceleration. The World Wildlife Fund is born in 1961, warning humanity early. In fact, 1968, Rachel Carson comes out with Silent Spring, the same warning. Dear friends, if we continue, we might end up in a situation that makes us losers. 1972, the Club of Rome comes out with the limits to growth, predicting that if we continue on this exponential rise on human pressures from biodiversity loss, overfishing, acidification, emission of greenhouse gases, we might be in the end receiving invoices from the Earth system. But it isn't until 1990 we see cod fisheries in Newfoundland collapsing. It's in 1990 we see, for the first time, we're passing 350 ppm. We've saturated the atmosphere. But still the economy delivers, and we're still not seeing the tipping points occurring until we see science being published here in 2000 onwards, having enough observations to show, oh yes, we're starting to see lake systems flipping in the United States from Steve Carpenter's fantastic work with eutrophication. We see the Baltic Sea flipping over into its anoxic dead state. We see the Arctic sea ice accelerating in the melting. We see suddenly abrupt changes starting to occur because now we have come to a point of saturation. But it's taken some time for science to put all the cards on the table. But dear friends, we are the first generation to have an empirical science that we've never had before, that we are at a point we have never been in before. Just as Sir David Attenborough pointed out, now is the time we need to recognize that everything we see here regulates the stability of the little marble Earth to keep it in a state that can support humanity. So, welcome to the Anthropocene. And that is a scientific, in my mind, most important message to humanity. That message has now been out for roughly 10 years. It was published the first time by Nobel Prize laureate Paul Crutzen, one of the scientists observing the depletion of the stratospheric ozone layer. Since then, we have a myriad of evidence coming out in policy, in media, in different parts of the world. You're of course aware that who decides what geological epoch we're in? It's of course in this country. So it is the Royal Geological Society, working right as we speak in the Anthropocene Working Group, laying out all the evidence on the table. And in fact, it will probably take a few more years before it's formally decided, but it's looking very clear that this is where we're heading. But as you see, there's more and more evidence on the table. And for example, The Economist, which I find as such an admirable United Kingdom journal, has this beautiful issue where it welcomes humanity to the Anthropocene just before the Rio +20 meeting, which was the birth of the process that led to the Sustainable Development Goals. And in that issue, it has this wonderful British understatement that we Nordics love so much. It says the follows, if I remember right now, it says, You know, when reality is changing faster than theory stipulates it should, a certain degree of nervousness is a reasonable response. Welcome to the Anthropocene. And in fact, it refers directly to science. So that is insight number one. Now, we have the Living Planet report aligning itself with that science. That in fact we are at this saturation point. We are, as Sir David Attenborough pointed out, entering the sixth mass extinction of species, the first one caused by another species. We have so much evidence about the very rapid decline in vertebrate species, in other species across the world, and the scientific evidence today that builds ecological functions, that builds ecosystem services, that builds human well-being. But you see, I would say that perhaps the most dire message to humanity is the following. So we have, in just 50 years, since we put in the high gear in mid-1950s until today, managed to push ourselves outside of a state that we've been in for the past 10,000 years, because that's when we left the last ice age. And now we are at a point that what we do in the next 50 years will very likely determine the state for humanity over the next 10,000 years. So we are at this pivotal point where we were part of the journey into what is now an unprecedented challenge, and we also hold in our hands the ability to steer ourselves into a manageable future for humanity. So it's 50 plus 50 determining the 10 plus 10,000. And that is the situation we're in right now. That's why the Anthropocene is so important, not as a tool to scare, but as a tool to act. And that is the situation we're in right now. And the world is starting to act. It is remarkable that in 2015, finally, policy, science, and business aligns itself and agrees upon the Global Sustainable Development Goals, which gives, for the first time, as we all know, an agenda for a desired future for humanity with aspirational, universal, social, and economic goals within global environmental targets for a stable and resilient planet. We've never had that before, and this is unique. So something is happening, to the extent, actually, I think that we can start talking of a new renaissance. A renaissance that says it's not a question if sustainable development is the future. The question now is, will we do it in time to avoid irreversible, abrupt, and potentially catastrophic change? And that is a big shift just in the last 5-6 years. Now, entering the Anthropocene, now we come to insight 2, means leaving the Holocene, the state that we learned in school that we've been in since the last ice age. And I will argue very strongly tonight that there's scientific evidence that the Holocene is a geological epoch, but it's also what we can call the Garden of Eden, the only state we know that can support humanity as we know it. And we have so much evidence here. And it comes from ice core data, and it's important to recognize that we have this library of the state of the planet, and it's so fantastic to stand on this stage with these beautiful systems showing how we oscillate between ice ages and interglacials through the Milankovic curves, which are here shown just for the past 500,000 years, showing the 100,000 years of ice age and the 20 to 30,000 years of interglacials, which we have had over the past soon 1 million years as far as we know in detail. What is remarkable and important with this curve is to understand that the interglacial states, we are in an interglacial right now, so you have the Holocene right at the right-hand corner, so we're in a warm interglacial state, that the range within which the planet remains in an interglacial state is only in the order of plus minus 2 degrees Celsius. In fact, for the Holocene, only plus minus 1 degree Celsius. And if we look past in history, we must now start recognizing and learning what were the conditions that can make the planet to remain in an interglacial state. And I'll come back to why we have to look backwards. But it's important to recognize, for example, that when we had an interglacial state the last time in the Eemian, the average temperatures on Earth was in the order of 2 degrees Celsius warmer than our pre-industrial levels, and sea levels were on average 6 meters higher. So this is a library that really gives us an indication of what we may be facing. But here comes the most important graph. So now I'll just take out the last 100,000 years, and it looks as follows. This is data from Greenland, so ice core data from the northern hemisphere, 100,000 years on the x-axis, and temperature variability on the y-axis, a good proxy of how it was to live on Earth. Now, this is a perfect choice of time, actually, because we have been modern Homo sapiens on planet Earth roughly 100,000 years. The cognitive revolution is estimated to occur at roughly 77,000 years. So we've had the same ability physically and intellectually to develop societies as we know them. But as we all know and just see from this graph, we had a jumpy ride indeed. We were hunters and gatherers. We were a few million people on planet Earth. We had, to put it very simple, a rough time. Actually, there's a cold point there, as you see, at roughly 78,000 years back, when most fresh water was tied up in the poles. We had sea levels almost 80 meters lower than today, and paleogenetic analysis indicates today that most likely we were down to less than 15,000 fertile adults at that point. We were hiding in the Ethiopian highlands, the only place where there apparently was biomass and fresh water to find, and we were, to put it simple, virtually extinct. It just tells us another thing, by the way, we're all very close family as a community. It could be good to tell people like Trump and ISIS. Now, this is a remarkable reminder of the fact that we depend on stable nature for our own human well-being. We leave the Ice Age and we enter the Holocene. And you can just see from the graph that this is a remarkable, not to say almost miraculously stable interglacial period. The temperature stays in its most extreme within plus minus 1 degree Celsius. Climate skeptics love to tell me that the Vikings grew grape on Greenland at 1100. Enormous variations. And then we had the little medieval ice age when the Swedish king invaded Denmark by walking the army over the ice in the Baltic between 1 plus minus 1 degree Celsius. That is the Holocene. And what do we do in the Holocene? Well, we barely enter the Holocene and we do the most important invention of all our inventions ever. We go from hunters and gatherers and we become sedentary farmers. And this is doubly remarkable because it wasn't a farmer sitting there in a corner having this Hevreka moment, seeing, oh my God, I can plant a seed. What a fantastic invention. And taking my mobile phone, which I didn't have at the time, to tell someone else that, look, try this. Oh no, we know for proof that we domesticated rice, wheat, teff, maize, sorghum on different continents roughly at the same time. And this is proof enough that we, as human beings, knew how to domesticate animals and plants, even before we left the Ice Age. But the conditions became so favorable. The rainy seasons established themselves. We suddenly knew year after year, if you were on a savanna, that it starts raining in mid-May and you have 20 rainfall events up until 100 days and then you can harvest. If you live in the northern temperature regions, you knew that the temperatures rose above 15 degrees Celsius roughly in spring, and it went on until the autumn took in. Everything we love, everything we depend on, from the biomes, the grasslands, the forests, the marine systems, the coral reefs, settle in the Holocene. The Holocene is what we love. The Holocene is what we care for. The Holocene is what we exploit and depend on. And that was the starting point, which then took us into the Great Acceleration in 1955 and the takeoff point until the 7.2 billion we are today, the modern industrial metabolism, where we are predicted to soon be 9 billion co-citizens on Earth in a globalized world. So if we take an ethical responsibility for our fellow citizens on planet Earth, I mean, we can live outside of the Holocene. We've done it before, a few million, hunters and gatherers. But if we take an ethical responsibility for 9 billion co-citizens, the scientific message becomes as simple as dramatic, that the Holocene is the only state of the planet we know for certain can support the modern world as we know it. So that, dear friends, is the key challenge. We are rapidly entering the Anthropocene, leaving the Holocene, but suddenly we have the scientific evidence to show that we depend on the Holocene. So that is insight number 2. The Holocene is our Eden's garden. And this is where we're heading, as we know. Here we have the Holocene journey, the plus minus 1 degree Celsius the last 2,000 years. Here we have the observational empirical evidence of temperature rise of anthropogenic greenhouse gas emissions. And here you have the journey we're heading towards. And this is even if we implement the INDCs adopted in Paris. So despite the tremendous achievement of understanding in the legally binding, since today I think it is, the legally binding Paris Agreement, that we need to stay as far below 2 degrees Celsius as possible, aiming for 1.5 degrees Celsius, even if we implement the intended national decarbonization plans, we would end up at 3 degrees Celsius, which is a place we haven't been for the past 5 million years. So this is the message too. We depend on an interglacial manageable state and to stay within those limits. The third insight is, well, if we're punching the planet, if we have filled up the entire natural biophysical space, if we are, so to say, pushing this pressure, how does she respond? And the interesting thing, and potentially even the dramatic thing, is that we have learned so well that she responds in two ways. One is that while she's strong, she takes the punches and buffers. So the Earth system has tremendous biogeochemical resilience, an extraordinary capacity to remain in the Holocene and take our stress. We have ample evidence of this. The most pedagogic and important one is that we emit 40 billion tons of carbon dioxide each year when we burn fossil fuels. Half of that, 20, is taken up by the oceans and on land as the world's largest free ecosystem service to the economy in the world. And that buffer is actually a direct response to the stress we're putting on the system, which is a proof that the Earth system is not only resilient, but is trying to, so to say, be our best friend to remain in the Holocene. But scientific evidence shows very clearly, since 30 years of advancements of complex systems analysis and resilience science, that in fact, long periods of slow change can very abruptly shift when a tipping point is crossed into abrupt and irreversible changes. And systems have multiple stable states. A rainforest can tip over and become a savanna. A savanna can tip over and become a steppe. A steppe can tip over and become a desert. And that what we have learned is that the reason why the systems have different stable states is the feedback mechanisms that keep them locked in their desired state, which is our Holocene state, or undesired states that do not support our well-being and economies. And this is the lessons from science over the past 30 years and a key third element of evidence. And we have such an enormous empirical base of knowledge here on Earth system tipping points that has been arising over particularly the last 30 years. And of course, one of the key areas of deep concern today is coral reef systems, where we're starting to see very dramatic shifts from the desired state where we have high degree of marine biodiversity, but with the combination of acidification, temperature rise, eutrophication, and overfishing, we see systems flipping over into these kind of situations where we know that the feedback mechanism is that you get soft, self-eutrophying algae taking over and self-reinforcing a non-functioning reef state, while the hard coral state keeps itself at low nutrients, high degree of oxygen, and in its, so to say, desired state through its own self-reinforcing feedbacks. We have now being able to map out across the world where are the risks of different tipping points that can occur in the Anthropocene. And the key message here is that these are not only climate tipping points. It's not only the risk of abruptly and irreversibly committing the Arctic sea ice to melting or the Greenland ice sheet to cross tipping points. It's also the big biomes such as the rainforests, such as the African savanna, such as the Indian monsoon system. We have so much knowledge today that these systems that we depend on, have been stable in the entire Holocene, are today at a shaky state where we could actually push them to a point of irreversibility. And it comes out in one graph, which I think is the strongest synthesis and key message in connecting the Holocene with tipping points, which was produced by colleagues at the Potsdam Institute of Climate Impact Research and delivered very recently in a paper just a few months back. So here you have the last 20,000 years. It's the 100,000 year graph, but taking an even shorter period. Temperature variability on the y-axis. You see we leave the Ice Age and we enter our Eden's Garden Holocene period. You see the plus minus 1 degree stability. Here you have the Paris Agreement, that if we actually deliver on Paris, we should stay below 2 and aim for 1.5 degrees Celsius. This is where we're heading. We know from the RCP analysis, the IPCC, that we're actually moving towards a 4 degrees Celsius warming path by the end of this century. But look now, here let's now put on the latest scientific evidence on tipping points. And these are only the climate-induced tipping points, and they look like this. And what you see here is on the bars, the uncertainty range in science, because there is an enormous complexity here and difficulty in putting the exact point where the biophysical tipping point is. But what I'll be focusing here is on this group, which is, as you can see from the uncertainty range, within Paris. So even if we deliver on Paris, what you see, and the most dramatic message, is what we know today on coral reefs is that even within the entire uncertainty range, they tip over even within the Paris range of 2 degrees Celsius. So there's no surprise that the 2015 El Niño event has led to the unprecedented bleaching events, even in the Australian coral reef systems, in the Australian Barrier Reef, because that's what science now shows clearly. Same goes for alpine glaciers, the Arctic summer sea ice. But look at Greenland, which has a wider uncertainty range, but even within Paris, we cannot exclude pushing the on button of irreversible melting of the Greenland ice sheet. It won't melt overnight, but it would be an irreversible on button that we, over the next 200-300 years, can no longer turn back. And that's one of the Brazilians' findings. Once you've crossed the tipping point, it's very difficult to go back, and we would then commit humanity to at least 7 meters sea level rise. The dark horse there is the West Antarctic ice sheet. Large uncertainty, but as you all know, we're starting to see more and more evidence in science of unexpected surprise, particularly in the Amundsen West Antarctic ice sheet, where we're starting to see melting and acceleration of that melting in even unexpected pace. So this is, in my mind, a key reason why we need a precaution and a humble recognition that we have really tipped into this big world on a small planet era. We are in the Anthropocene. We must do everything we can to remain in a stable interglacial state, and tipping points is part of reality. We see these tipping points now being mapped in different systems across the world. I won't go through that in detail, just to say that there's so much empirical evidence today. Here are just the latest Arctic resilience assessment that we have led for the Arctic Council, showing that we can today map out 19 tipping points that are at risk of occurring in the Arctic, from steppe tipping points to kelp tipping points, from Arctic sea ice losing its albedo, which means that it absorbs and self-reinforces warming. That's the feedback, by the way. A white surface is self-cooling by actually sending back up to 90% of incoming heat back to space. A dark surface absorbs 80% of heat. That's the self-reinforcing feedback shift. Boreal forest losing carbon sinks. We start seeing the first evidence of methane release in permafrost in the Arctic. We start seeing shifts potentially even in the steppe ecosystem that hold massive, hundreds of gigatons of carbon in its upper root zone. But the key message here is that these systems don't operate in isolation. They're teleconnected to systems across the world where we no longer can exclude connections to eutrophication in lake systems in tropical regions. Savanna systems affected by the monsoon teleconnections with the Arctic in terms of weather patterns. How we can no longer exclude that different mangrove systems in tropical coastal regions, due to bleaching and warming, are connected to the Arctic glacial system, and soil acidification can no longer be disconnected. So to put it simple, we are in an interdependent world where every biome counts, every ecosystem counts, not only for the community that depends directly on it, but for our well-being everywhere. I actually, as a scientist, which of course sounds a bit dramatic, but I have actually even communicated to my finance minister in Sweden that we have scientific evidence to say that you as a finance minister should be equally concerned of the GDP and the job creation within your national borders as you should be on the stability of the Arctic, of the rainforest, of the coral reef systems, and on the savannas, because they give feedbacks lending the stability of the Swedish financial economic system. And I think this is the kind of integrated science we're today starting to see evidence from. And I could go on very long time showing, and we've learned a lot from WWF, not least, on ecosystems that have these bistable states with different flips between systems. And the red thread is very clear. we have tipping points from desirable to undesirable states that do not support human well-being. So I'll take a pause here just to say that this leads to an equation. It leads to what I think is the most important equation that we have today, that the Anthropocene plus the recognition that the Holocene is an interglacial state we depend on, plus tipping points equals planetary boundaries. Meaning that the empirical evidence of the exponential rise in pressures, the empirical evidence that an interglacial state of the planet is our desired state, and the insight that nonlinear dynamics cannot be excluded leads to the natural conclusion scientifically that that means that we should actually try to answer two questions. Question one must be, what are then the environmental processes that can actually keep the planet in a desired, manageable interglacial state? And can we, for these processes, even quantitatively, define boundaries that would give us a safe operating space, which would give our ability to keep the planet, our small planet, in an interglacial state? And that is, dear friends, the theory on planetary boundaries. So planetary boundaries did not come out of the blue. It was an incremental, natural ability, and I'm standing at this Royal Society place, so I'll quote Isaac Newton, standing on the shoulder of giants, taking the next incremental step of remarkable Earth system science advancements since the 1970s. And that takes us to this big question. Does the planet have multiple stable states? I mean, if the ecosystems have it, does the planet have different states? And we know today that the answer is yes. The planet can be in an interglacial state, it can be in a glacial state, but it can also run away into a hot state, which it hasn't been in for the past 50 million years, but we might be triggering it irreversibly out of a desired state. And we have evidence of a little shaky journey towards this situation, actually. This is science coming out just the last year, a part of the Anthropocene Working Group, showing, you recognize it now, we leave the Ice Age, we enter the Holocene, and these are the projections to the future of the different journeys according to the RCP scenarios. You have in red there, which is our end of this century projection under the RCP 8.5, which we're following now, the 4-degree point. The upper point there is that just because we arrive at 2100 doesn't mean that the planet has reached a new equilibrium. The new equilibrium is most likely even higher up at 8 degrees Celsius. But the key of this paper was the conclusion that we've probably created so much instability, and we've created so much human-induced climate forcing, and we've undermined so much of the biosphere that the door to the next ice age is closed. No, the door to the Holocene is closed, meaning that we have actually undermined the Earth system so much that it's not possible for us to go back to the Eden garden that we depended on. So this is coming out just 2016, the recognition that already at 1 degree Celsius, we may be outside of the Holocene. And that is why I flagged before that we need to look at the other interglacials to say, how far beyond the Holocene then can we push before we go outside of even an interglacial? So the key message here is that it's a dire one, but it's an important one, that there's no such thing as saying, oops, we've done some mistakes, let's solve them and go back to how it was before. No, the key message from science today is the door is still open to solve this. We can transform ourselves to a manageable future, to remain in an interglacial state, but there will be some costs. There will be some adaptation. The species lost are lost. We cannot get them back. And that the door to the Holocene as the virgin state is actually closed. The other dramatic conclusion came from a paper just a few months later than that, showing that even the door to a glacial period is closed. That we have raised climate forcing so much that it's very unlikely that we could see a natural distance between the planet and the sun taking us back into a glacial period. So we have, so to say, cynically, that could be kind of a cynical good news of climate change, by the way, I realize, that there's no more ice age. Forget about that. We'll stay in an interglacial, or it's warm or really warm, but it won't be cold. And that means that the drama is that there's only one or two doors open. The door that we need to aim for, which is a manageable interglacial. It might not be the Holocene, but how far can we go to stay within something that is still interglacial? Or the drama door, the door that would kick off irreversible tipping points that could take us to 4, 5, 6 degrees Celsius outside of the Holocene. And that is why we came up with the planetary boundary science, to try and define the boundaries within which we can actually remain in a manageable interglacial. That gave the 9 systems that we have identified as regulating the Earth system. It's not only climate, it is also the 4 slow variables that determine nature: freshwater, biodiversity, the 2 nitrogen phosphorus cycles, the nutrient cycles on planet Earth, and the whole freshwater hydrological cycle. And also includes the alien processes of aerosols, air pollution, and chemicals, and of course the protective stratospheric ozone layer. And in green, what you get here is a safe operating space. And we've been able to quantify now 7 of the 9, and science is continuously going on to perfect this definition. And as you see, we are in a danger zone and transgressing 4 of the 9 boundaries. Yellow means we're still in the uncertainty range of science. Red means we're in a really danger zone. And it's for biodiversity and eutrophication. Climate is still in this uncertainty range, but we're seeing, as you have already experienced, but also from this lecture, see that we're starting to see the potential drama that is occurring already at 1 degree warming. This tool gives us something that can function as a roadmap for humanity. And interestingly, it gives us also a journey of history. So this is where we were when James Watt invented the steam engine in 1750. We were right at the center of the safe operating space. Already in the 1950s, after the Haber-Bosch process invention and the expansion of modern agriculture, we flipped out already then, initiating what is about to become the 6th mass extinction of species. But you see, we're still in the safe operating space for all boundaries. We're still a small world on a big planet. Then we come to the 1970s. So this is where WWF is born, Rachel Carson gives her warning, the limits of growth comes out. But these are early warnings because there was no empirical evidence to suggest that we could knock the planet off its course. We were still in the safe operating space. These were insightful early warnings and insightful efforts of becoming planetary stewards. But look at this. Then, bang, in 1990, we fill up the whole space and we start truly transgressing boundaries. And what you see here, which is a really important insight, is that we go right out into the red on stratospheric ozone depletion. But remember, science identified this in the early 80s. In 1987, the Montreal Protocol was signed. Policy listened to science. Nobody had ever seen an ozone hole, but the warning was taken seriously. The convention was signed, business got to work, and the situation today is we're back in the safe operating space on stratospheric ozone depletion, and we have evidence showing that we're starting to get back towards a stable stratospheric ozone layer. This is the current situation. You start to see that we're filling up all the space, but that we're also in a danger zone on several of the boundaries. So that is, to say, the message in terms of aligning itself with the Living Planet report. Now, we have taken this work into a scientific journey on what does this all imply for the way we can become planetary stewards. And one big shift is that you all remember, and WWF has been very deeply involved in trying to do the best you ever can on how we manage our global commons. The global commons was born in the 1960s, 70s, identified as the atmosphere, Antarctica, space, and the high seas. You know, everything that was not in the national borders of a nation state, which was externalities and global commons and things that nobody owned, we somehow had to have some form of moral responsibility for. The latest science that we've now produced and reported to the Global Environment Facility and a whole bunch of other organizations is that we now need to rethink the global commons. We have the recognition that now we depend on all the big biomes on planet Earth. There's no such thing as a common or an externality out there. All the biomes build up the components of the resilience and the ability of the Earth system to support humanity. So the rainforest and the ecological functions and carbon sinks and the whole biodiversity and the marine systems, the phenomenal ice sheets that reflect incoming heat and keep sea levels at bay, even the temperate forests with their color and albedo and the carbon sinks, the savanna systems are all fundamental in keeping the Earth system in a manageable interglacial. And it means that we propose 3 new principles of how to manage global commons in the Anthropocene. That we now need to recognize principle 1, that there is no such thing as externality any longer. We can no longer, in any macroeconomic analysis, in any societal kind of policy making, consider that this is what we own and are responsible for, and what is out there is somehow things that can be exploited and receive our pressures. It's exactly the reverse, that now we need to internalize everything inside our own models, because we are now truly at this saturation point. Principle 2 is the Universality Principle, that if we're a big world on a small planet, and if we depend, all of us, equally on all nature on planet Earth, then we must apply a moral, equitable sharing of the remaining beauty on Earth. We simply must recognize that there's a per capita right to nature, but there's also a per capita responsibility for nature. And the final principle, not surprisingly, coming from the Stockholm Resilience Center, is resilience. That we now need to recognize that a precautionary principle, a humbleness, stepping back one step and recognizing that we cannot push ourselves to efficient optima. Rather, we need to understand the need to back off and have abundance, flexibility, and diversity as key golden rules for navigating the future. And this has also been so well empirically mapped today. The resilience theory started in the early 1970s and has been now coming up to the surface with so much evidence. And we have, for example, mapped out the 7 principles for resilience building. I won't go through the 7, but the number one red thread is that there's so much empirical evidence today that biodiversity and social diversity is what builds strong ecosystems and strong societies. And it applies for how you save your money in different financial mechanisms to how many pollinators you have in your agricultural landscapes. And this is a key message which is so basic for us in this room, but it has to be understood in the big scheme of things. And again, the Living Planet reports shows the risks we're taking when we are moving so fast in a pathway that may lead to fundamental extinction, losing this diversity, which again, of course, can be protected solely on ethical grounds, but it now also must be protected on rational, economic, and well-being grounds. So we have identified 4 transformational journeys that we now need to urgently embark on, meaning that we are at this dire juncture, we are transgressing boundaries, and we need to transform ourselves rapidly so we can come back in a manageable, stable state of the Earth system. There's much more than this, but we find evidence to support that decarbonizing the energy system is potentially the number one most urgent pathway for humanity at this point. That we need to transform our unsustainable food system to healthy, sustainable agricultural systems, which by the way means no more expansion of agricultural land, because that's the number one driver behind loss of species. We have so much evidence that we need to transform into sustainable urban systems, with soon 75% of citizens living in urban regions. And finally, we need to break the linear economic model and have circular models that works in tandem and in harmony with the planet. And that is, I think, one key message to show that this is a tipping point towards a logic where sustainability within a safe operating space of planet Earth, the Living Planet Report message, is our guiding principle. And we have very tangible pathways. And in fact, as we all know, we can start filling these with empirical proof that, in fact, the solutions are largely available. So this means a new mindset, going from linear incremental to exponential. And we've talked so much, scientists, of our exponential journey in the wrong direction. Now we need to start talking about the exponential journey in the right direction. And that is often forgotten, that exponential curves, they tend to, you take the first step, nothing really happens. You take the second step, not much more happens. The third, and not much more happens. But then you start really moving into an exponential rise. And we tend to forget how rapidly things can change. The fact that if we take 35 steps here, we only go, if we go linear, out of this room. But if we take 35 exponential steps, we end up on Mars. It's quite a difference. When things start doubling, thanks to innovation pathways and recognition of new opportunities, things can actually change in a remarkably fast way. And that we now need to start finding these solutions and putting pressure and giving incentives and seeing what I start finding so exciting with young people in the world, that environment and sustainability is no longer the sacrifice. It's actually the high-tech, advanced, Tesla cool future. That can be the exponential takeoff point, where sustainability is the cool thing and the coal mine is actually going back to the cave. But I remember just 10 years back, it was the reverse. I, as an environmental scientist, was the one propagating going back to something backwards. So we have all the empirical evidence that things are starting to happen. And it's just remarkable because we know that this is probably just the early stages of the wind power, the solar voltaics, the shifts in the cost of battery capacities, the fact that, you know, just in the Paris car show last 2 weeks, how big car company after big car company, the Detroit huge companies, are actually launching their family electric $30,000 300-kilometer cars in 2017, 2018. Tesla might be beaten on the journey towards the exponential rise. Who knows? We might be the first generation to know the problems, but we might even be the first generation to actually be able to tell our kids, you remember when we put gasoline in our cars? Those were the days, you know? So this might be actually an exponential journey that takes us into something that we recently published in Science that we call, we may need a global carbon law. The Moore's law that was set up in the computer industry of the 18-month doubling of processor speed became a self kind of delivering prophecy. Now we are suggesting that we should actually launch a carbon exponential law, a law that goes as follows. It's just been published in a journal called Earth's Future, that we should try to halve global emissions every decade. That's an exponential curve that can take us to decarbonizing the world economy by mid-century. And this is the key graph in this presentation, in this article. This is the first time, you know that the IPCC, the Intergovernmental Panel on Climate Change, has launched its 1.5 degrees Celsius report to be finished 2018. This is the first effort actually to fast-track that, to summarize what do we know today from all the global climate models in terms of what Paris really means. And what you have here is a carbon law. What you see here is time on the x-axis from now till 2100. You see 2050 in the middle. Here are emissions on the y-axis, the 40 gigatons that we emit today up at the top. And message one is, because the curve you see here is the pathway we need to follow with fossil fuel emission reductions. And what you see is we need to bend the curve of emissions no later than 2020, in 4 years' time. And then rush down at an exponential reduction pace, which is halving emissions every decade. It's a pace of 6 to 7% reduction every year to reach a decarbonized or net zero carbon world economy by mid-century in 34 years. This is the most rapid industrial revolution we've ever seen. It's much more rapidly than when we entered the modern industrial era. But that's not enough. Even if we would decarbonize the world economy at this pace, what you see in blue and green here is nature. This is the Earth Resilience free subsidy to the world economy, with the roughly 20 gigatons of carbon being taken up by oceans in blue and natural ecosystems on land in green. You see that this sink needs to be sustained, which means that there is no Paris Agreement unless we take care of biodiversity and nature, because we need the resilience in the ecosystems on land and oceans to have any chance to deliver on Paris. You see that the brown part in the beginning is agriculture, a net source of emissions. By mid-century, you see it goes and becomes negative. So it's a transformation to an exponential shift into sustainable intensification, where all the food goes from source to sink. And then comes the real drama. The yellow part there is the recognition that there is no such thing as us being able to deliver on 1.5 to 2 degrees Celsius without us investing also in CCS. The yellow part there is the recognition that when our emission of greenhouse gases go down, means that concentration of carbon dioxide molecules in the atmosphere also goes down, which means that nature does not have to play its resilient role as intensively as before. That's why the blue and green goes down, and needs to be compensated by CCS and BECCS, biological and engineered carbon capture and storage. Now, what happens if we do all this? We decarbonize the fossil fuel system by mid-century. We take care of all the nature so it's resilient and keeps its carbon sinks up. And we even scale up CCS and BECCS. We do all of this. And still it gives us only, according to what we know today, a 66% chance of delivering on Paris. a 2/3 chance. So if this is not enough to tell the world, dear friends, we are in a transformational journey. We need to really pull up our sleeves to move towards something new. And that new has to be very new, because even in its best sustainable thinking, it looks like this. This is the real 1992, 3 pillars of sustainable development: the human, the natural, and the economic capital sustainable development. We must now admit it didn't work. It became a Mickey Mouse economy. The economy grew at the expense of human capital and natural capital. And it's time to shift over into a new situation where we actually see the economy delivering for society within a safe operating space of planetary boundaries. And the Sustainable Development Goals has it all. The 17 goals that includes both the social, the economic, and the biophysical. The problem is, as you certainly recognize, that these are now seen as a Swedish smorgasbord. You pick the goodies you want, and then off you go and you do the best you can on goal 1 or goal 7 or goal 4. But we would argue scientifically that we need to think of them in this way, that there is in fact an integrated systems whole for our 17 Sustainable Development Goals. We have the 4 planetary boundaries, goals 6, 13, 14, 15, biodiversity, climate, oceans, and freshwater, which form the non-negotiable biophysical platform for a stable interglacial planet, where we have our aspirational social goals, we have our economic tools to deliver on those social goals, and we need partnerships and trust among nations in the world. And that this is, I would argue, the key message from our insights on sustainability science over the past decades. And that is the only way to give us a world in 2050. And that world in 2050 is about delivering on the Sustainable Development Goals. But remember, that is just in 14 years. That is 2030. And we cannot fast track and just deliver that in unsustainable ways. We must think all the way until end of this century to target transformations where we remain on a stable and resilient planet Earth system. So the SDGs cannot be thought of as a short-term kind of MDG plus agenda. It must be a future where we reconnect once and for all with planet Earth. It is kind of shifting from Mickey Mouse to a wedding cake. And dear friends, I think that's my key scientific message to you. Thank you very much.